Hello everyone and welcome to our channel, Mootechie. It's wonderful to have you here as we dive into a fundamental and fascinating topic, the ionic product of water. Get ready to unlock the secrets of pH and understand what makes water so special. Now, let's begin our journey with the autoionization of water. Did you know that water molecules are constantly talking to each other? In a process called autoionization, one water molecule donates a proton to another. The chemical reaction looks like this. Two H2O in the liquid state are in equilibrium with H3O+ in aqueous solution and OH- also in aqueous solution. This is essentially a proton transfer between two water molecules. It's crucial to know that this process occurs to a very small extent in pure water. At 25 degrees Celsius, the concentrations of both hydronium and hydroxide ions are a tiny 1.0 times 10 to the negative 7 molar. Let's highlight some key points. The equilibrium position lies far to the left, meaning the reactants, the water molecules, are heavily favored. However, both ions are always present in any water-based solution. Their product, the concentration of H3O+ times the concentration of OH- is constant at a given temperature. And this very autoionization is what establishes the basis for our entire pH scale. To visualize this, imagine two water molecules. One acts as a proton donor, the other as a proton acceptor. After the transfer, you're left with one hydronium ion, H3O+, and one hydroxide ion, OH-. And remember, at 25 degrees Celsius, both of these ions are present at a concentration of 1.0 times 10 to the negative 7 molar. Now, let's define the ionic product of water, Kw. The ionic product of water, Kw, is the equilibrium constant for water's autoionization. It's defined as Kw equals the concentration of H3O+ times the concentration of OH- at a given temperature. At 25 degrees Celsius, Kw equals 1.0 times 10 to the negative 14. Its logarithmic form, pKw, which is negative log of Kw, equals 14.00. In terms of units, it's technically unitless when using activities, but we often treat it as having units of molar squared when using concentrations. Where does this come from? Let's derive it from the autoionization reaction. From 2H2O liquid in equilibrium with H3O+ aqueous and OH- aqueous, the full equilibrium expression would be Kc equals the concentration of H3O+ times OH- divided by the concentration of H2O squared. Since the concentration of water itself is nearly constant, a massive 55.5 molar, we simplify this by defining Kw as Kc times the concentration of H2O squared. This gives us our clean final expression. Kw equals the concentration of H3O+ times the concentration of OH-. So, to reiterate, Kw equals H3O+ times OH-. At 25 degrees Celsius, Kw equals 1.0 times 10 to the negative 14. The logarithmic form, pKw, equals negative log of Kw, which is 14.00. And in pure water, at 25 degrees Celsius, the concentration of H3O+ equals the concentration of OH-, which equals 1.0 times 10 to the negative 7 molar. Let's represent this water equilibrium more clearly. The full equilibrium expression is Kc equals H3O+ times OH- divided by H2O squared. But since H2O is nearly constant at 55.5 molar, we simplify to the famous equation Kw equals H3O+ times OH-. We can also set up an ice table in pure water. Initially, we have about 55.5 molar of water and close to 0 molar of both ions. The change is minus X for water and plus X for each ion. At equilibrium, water is at 55.5 minus X and both ions are at X. At 25 degrees Celsius, X squared equals Kw, which is 1.0 times 10 to the negative 14. Therefore, X equals 1.0 times 10 to the negative 7 molar. So, H3O+ equals OH- equals 1.0 times 10 to the negative 7 molar. The key points here are that pure water autoionizes to establish this equilibrium, and the equilibrium strongly favors water molecules, which is why Kw is so very small. Visually, you see two water molecules on one side and the ions on the other, with the equilibrium arrow pointing strongly back towards the water. Next up, let's explore the relationships between pH, pOH, and Kw. We define pH as negative log of the hydronium ion concentration. We define pOH as negative log of the hydroxide ion concentration. And the beautiful relationship that ties it all together is pKw equals pH plus pOH. At 25 degrees Celsius, pKw is 14.00. This gives us our general relationships pOH equals pKw minus pH, and similarly, pH equals pKw minus pOH. Here's a crucial tip for significant figures. The number of digits after the decimal in a pH or pOH value equals the number of significant figures in the original concentration. For example, a pH of 4.30 means the hydronium ion concentration is 5.0 times 10 to the negative 5 molar, which has 3 significant figures. So, to summarize mathematically, pH equals negative log of H3O plus, pOH equals negative log of OH minus, and pH plus pOH equals pKw, which is 14.00 at 25 degrees Celsius. On a scale, as pH goes from 0 to 14, pOH goes from 14 down to 0, with them crossing at 7. Now, what do these values actually mean? Let's define neutral, acidic, and basic solutions. A solution is neutral when the concentration of hydronium ions equals the concentration of hydroxide ions. At 25 degrees Celsius, this means pH equals pOH equals 7.00, but this shifts with temperature. A solution is acidic when the hydronium ion concentration is greater than the hydroxide ion concentration, which means pH is less than pOH. A solution is basic when the hydroxide ion concentration is greater than the hydronium ion concentration, meaning pH is greater than pOH. Always remember that Kw equals H3O plus times OH minus equals 1.0 times 10 to the negative 14 at 25 degrees Celsius. And remember, neutral pH is not always 7.00. Let's look at some common examples. Acidic examples include vinegar with a pH around 2 to 3, lemon juice at about pH 2, and stomach acid around 1.5 to 3.5. Neutral examples are pure water at 25 degrees Celsius with a pH of 7, human tears around pH 7, and blood, which is very close to neutral at about 7.4. Basic examples include seawater at about pH 8, baking soda around pH 9, and household ammonia at about pH 11. To visualize the ion balance, in an acidic solution like vinegar, hydronium ions far outnumber hydroxide ions. In a neutral solution like pure water, they are equal. In a basic solution like baking soda, hydroxide ions are much more abundant. Now, this brings us to a critical point, the temperature dependence of Kw. The autoionization of water is an endothermic process, meaning it absorbs heat. Because of this, Kw increases with temperature following Le Chatelier's principle. Let's look at some typical values. At 0 degrees Celsius, Kw is 1.14 times 10 to the negative 15, and the neutral pH is 7.47. At 25 degrees Celsius, it's the familiar 1.0 times 10 to the negative 14, and a neutral pH of 7.00. At 50 degrees Celsius, Kw rises to 5.47 times 10 to the negative 14, and the neutral pH drops to 6.63. And at 100 degrees Celsius, Kw is 5.10 times 10 to the negative 13, with a neutral pH of 6.14. The key formula to remember is that the neutral pH shifts with temperature and is equal to pKw divided by 2. This is incredibly important for biological systems and chemical processes that occur at non-standard temperatures. If we were to plot temperature against pKw, we would see a clear downward trend. As the temperature increases from 0 to 100 degrees Celsius, the pKw value decreases from around 15 to about 13, showing that the ion product is becoming larger. All right, it's time for some worked calculations to put all this theory into practice. Here are the key equations we'll use. The ionic product, Kw, equals H3O plus times OH minus. The pH definition equals negative log of H3O plus. The pOH definition equals negative log of OH minus, and the core relationship pH plus pOH equals pKW at 25 degrees Celsius. kW is 1.0 times 10 to the negative 14, and pKW is 14.00. Some important tips before we start. Always use the correct kW value for the given temperature. Remember the significant figures rule. To find H3O plus from pH, you calculate 10 to the negative pH. To find OH minus from pOH, you calculate 10 to the negative pOH. And never forget that neutral pH is only 7.00 at 25 degrees Celsius. Let's try example 1, finding H3O plus and pH at 25 degrees Celsius. We are given that the hydroxide ion concentration is 2.0 times 10 to the negative 5 molar at 25 degrees Celsius. Step 1. Calculate pOH. pOH equals negative log of the OH minus concentration, which is negative log of 2.0 times 10 to the negative 5, which equals 4.70. Step 2. Calculate pH. Since pH plus pOH equals 14.00, pH equals 14.00 minus 4.70, which is 9.30. Step 3. Find the hydronium ion concentration. H3O plus equals 10 to the negative pH, which is 10 to the negative 9.30, which equals 5.0 times 10 to the negative 10 molar. Alternatively, we can use the kW expression. H3O plus equals kW divided by OH minus, which is 1.0 times 10 to the negative 14, divided by 2.0 times 10 to the negative 5, which also gives us 5.0 times 10 to the negative 10 molar. Both methods confirm our result. Now for example 2, finding OH minus and pOH at 25 degrees Celsius. We are given a pH of 5.20. Step 1. Calculate the hydronium ion concentration. H3O plus equals 10 to the negative pH, which is 10 to the negative 5.20, which equals 6.3 times 10 to the negative 6 molar. Step 2. Calculate pOH. pOH equals 14.00 minus pH, which is 14.00 minus 5.20, giving us 8.80. Step 3. Find the hydroxide ion concentration. OH minus equals 10 to the negative pOH, which is 10 to the negative 8.80, which equals 1.6 times 10 to the negative 9 molar. Again, the alternative method works too. OH minus equals kW divided by H3O plus, which is 1.0 times 10 to the negative 14, divided by 6.3 times 10 to the negative 6, which also gives 1.6 times 10 to the negative 9 molar. Perfect. Finally, let's tackle an example at a different temperature. Example 3, a different temperature of 40 degrees Celsius. We are given that kW at 40 degrees Celsius is 2.92 times 10 to the negative 14, and we have a solution with a pH of 7.00. Step 1. Calculate pKW. pKW equals negative log of kW, which is negative log of 2.92 times 10 to the negative 14, which equals 13.53. Step 2. Calculate the pOH for our solution. pOH equals pKW minus pH, which is 13.53, minus 7.00, giving us 6.53. Step 3. Find the true neutral pH at 40 degrees Celsius. pH neutral equals pKW divided by 2, which is 13.53 divided by 2, equaling 6.77. This is a fantastic insight. It means that at 40 degrees Celsius, a solution with a pH of 7.00 actually has a slight excess of hydroxide ions, making it a slightly basic solution. And there you have it. Let's wrap up with a summary of the key takeaways. The ionic product of water, Kw, equals H3O plus times OH minus. At 25 degrees Celsius, it's 1.0 times 10 to the negative 14, and pKw is 14.00. Neutrality shifts with temperature, and the neutral pH is always pKw divided by 2. The core relationship pH plus pOH equals pKw must be used with the appropriate Kw value for the temperature. In acidic solutions, hydronium ions exceed hydroxide ions, so pH is less than 7 at 25 degrees Celsius. In basic solutions, hydroxide ions exceed hydronium ions, so pH is greater than 7 at 25 degrees Celsius. For your calculations, remember the logarithmic formulas and the significant figures rule. And just be mindful that technically, equilibrium constants use activities, but we often use concentrations for simplicity. So, to put it all on a final visual, Kw equals H3O plus OH minus. pKw equals pH plus pOH, and at 25 degrees Celsius, that sum is 14. Thank you. See you in the next class.